So now we're in chapter 17. Right, we finished chapter 16 with acids and bases, and now we're moving on to aqueous ionic equilibria. So somewhat of a new topic, but at the same time, we really are still talking a lot still about acids and bases and their conjugates, conjugate bases and conjugate acids. So just to kind of review from chapter 16, remember the identification process is most important here for realizing what type of system you have. We've talked about, strong acid, a strong base type questions from chapter 16, right? Remember that told us that we have to follow complete dissociation of that strong acid and strong base to then determine pH. We then got into weak acids, weak bases. Remember, kind of a distinction was this idea of a Ka or a Kb. So here's where we have an equilibrium, and we tended to follow the assumption method. And then at the end of chapter 16, we got into the weak side of the conjugate side of the coin, as far as weak conjugate bases and weak conjugate acids. Remember, with this one, we had to do the Ka, Kb shuffle, right, to be in terms of the conjugate, and then it was just the same idea as far as then equilibrium and assumptions. So that's what we did in chapter 16 as far as identifying all these different types of acids and bases, and then determining how we can figure out pH and solve these pH type questions, either based on complete dissociation or equilibrium and assumptions. Now getting into chapter 17, the first topic is buffers. And buffers is really just a combination of points 2 and 3 that we just discussed. A buffer initially contains now both the weak parent and its conjugate, or its weak conjugate. This is initially, that's the biggest point that I could address here in that recognition. Above, with chapter 16, we initially began with the weak parent, or we initially began with the weak conjugate in terms of those equilibrium-based questions. With the buffer, the new addition here is now the combination of both of those ideas, that now we don't have to begin just with weak parent or weak conjugate. We can actually begin with both, right? So that recognition skill here is still being applied, right? That now we have to recognize that, oh, I have both of these things initially, and now that is a buffer. Buffers have basically the ability to keep constant pH of a particular solution. So that's why we use it a lot, and that's why buffers are used in all areas of science. We're often trying to replicate, the actual biological system, and our biological systems are buffered. Your blood is buffered with a carbonic acid type buffer to have a pH of 7.4. If your blood's pH starts to drop or starts to increase, things are not good for you. Okay, so certain processes in our body are very much pH dependent. So having a buffer allows that pH to remain constant. Now, how does the buffer actually do that? Well, it does it through basically a neutralization reactions. So buffers have the ability to keep constant pH of a solution by using a neutralization process. So what does that mean? That means that buffers have the ability to neutralize exogenous acid and base. As far as exogenous, it just means it's just this added type of base, added acid or base. In your cells are also buffered, and there's actually a lot of what they call proton waves or proton currents, where to help signaling of certain enzymes, the pH of the cell has to drop or raise in order to activate a certain process. However, that can lead to then cell apoptosis or cell death. So what the cell has is this buffered system in order to maintain the cell's lifetime, that even though we have these proton waves or proton bursts within the cell, if you will, that the cell then doesn't allow that to really screw up all of the mechanics that are operating in the cell. It has the ability to neutralize that extra acid or extra base, that exogenous acid or exogenous base that's actually being produced. All buffers have what is known as a buffer capacity. And this is just its ability, to neutralize strong acid or strong base additions without a change in pH. If that pH, or if the pH of the solution changes by more than 1 pH unit, then you are beyond the buffer's capacity. And that's simply a mole game. We're talking about a neutralization reaction, so we're talking about mole equivalents of the buffer versus mole equivalents of the strong acid that's added or the strong base that's added. So if you swamp the buffer with strong acid or strong base, well, then you kill its capacity. You're going to overwhelm it, and as a result, the pH will change drastically. So you got to make sure your buffer has enough capacity, enough moles of both the parent and the conjugate to handle the strong acid or the strong base that's either being produced in the experiment or added in the experiment or, produced biologically. So those are a couple of different terms, right? We have our buffer definition, right? Combination initially of a parent and its conjugate. Buffers are used basically to neutralize strong acids or strong bases without a change in pH. And all of these buffers have a certain buffer capacity, which is how much of that strong acid or strong base it can neutralize. So how do we look at buffer equilibria? So far from chapter 16, we've always wrote our equilibrium reaction in terms of what we are starting with initially. But here, now we're starting with two things initially. So how does that affect our setup of the equilibrium reaction? So for buffer equilibria, the equilibrium is always written as the parent being the starting material and the conjugate being the product. So basically we can say that this is in terms of the parent. So we set up our equilibrium reaction just like we would set up a parent equilibrium reaction. So as an example here, a combination of acetic acid and sodium acetate constitutes a buffer, right? We have a combination of here the acetic acid, that's our parent acid, and then we also have our sodium acetate, and that is the conjugate base of that parent acetic acid. So again, that equilibrium reaction is in terms of the parent. So when I'm writing my equilibrium reaction, I just want that equilibrium reaction to have that starting material be the parent. So I have my parent acid, the acetic acid, on the starting material side. I have it reacting with water, which we've seen many times in chapter 16. We have an equilibrium process that then produces our acetate, but we already have that initially, and also hydronium ions. So it's very much in terms of how the parent would react. So here is our parent acid, and we have an initial concentration of it, and here is our conjugate base, and we also have an initial concentration of it. So that's the big change again, not just one or the other, but having both. Now that we have that equilibrium set up, right, we realize that now that's just a Ka that's describing that process as far as its equilibrium constant. And now we can do all the same things that we've done in the past from chapter 16 as far as setting up our equilibrium reaction, which we just did, setting up what Ka is equal to, putting our ice table together, and solve this much like a normal weak acid or weak base style question. So our Ka from the reaction above would be the conjugate times hydronium ion in the numerator all over our parent acid in the denominator. And so that would allow us now to set up our ice table. We'll find that there's a trick that we can use, but to begin, let's just kind of reinforce what we learned in chapter 16. So now constructing the ice table, putting in all the components that are necessary for Ka. So we have the parent acid, acetic acid, the conjugate base, acetate, and then hydronium. And so initially, we are going to have an initial concentration of both our acetic acid and our acetate, but we will not have a concentration of hydronium ion. So that's the sign or the flag, right, to tell us which direction change has to go towards in order to reach equilibrium. So that means we would have positive change for the products in both the acetate and the hydronium ion, and we would have negative change for the parent acid, the acetic acid, all 1 to 1 to 1. So at equilibrium, we would have basically our initial concentration of acetic acid minus X, our initial concentration of acetate plus X, and then we would have X for the hydronium ion. And remember, that's always our angle to get to pH, right? That if we can figure out what X is, that's the concentration of hydronium ion at equilibrium, and then we can take the negative log of that to then define the actual pH of the solution, in this case the pH of the buffered solution. So here's where we would then substitute back into our Ka. Right, our Ka, just to remind us, would be those products, right? The acetate, the hydronium ion in the numerator, over the acetic acid. And now we're substituting in those equilibrium values that we got from the ice table. So our acetate would be that initial concentration of acetate minus X. Our hydronium ion concentration would simply be X. And our acetic acid would be that initial concentration of acetic acid minus X. I apologize, there's an error up there in the numerator. That should be not initial concentration minus X of the acetate, but actually plus X. So make sure we change that. So now, what will we do? Well, we would either try to use simple algebra, such as a square root, to solve, but obviously we can't do that with this style of question. We would have to use the quadratic or assumptions at this point. So I'm going to choose that assumption motif where our Ka is going to be less than 1 times 10 to the negative fourth, and that's going to be a constant for us within this chapter. And we have initial starting material, which we have here as well. So we're really set to make an assumption, process. So if I rewrite the equation, right, with the values of concentration minus X or plus X, like we see here, now I'm making that assumption, right, that if I have a small k and I have initial starting material, I can say that that X value is small or 0 relative to the initial change, because there isn't going to be much change that's going to really impact that large concentration. It's numerically insignificant. But not only can I do it with that particular X as far as that initial concentration of the parent acetic acid, I can also do it with any other initial concentration I have, namely the concentration of the conjugate base acetate. So those two X's are actually going to drop out. And so we find our Ka is going to be equal to that initial concentration of acetate times X, which again is our hydronium ion, over the molarity initially of our acetic acid. So that is how we could then solve for X for hydronium, and then obviously we can get to the pH by taking the negative log of that hydronium ion concentration. I'm sure you'd be happy to hear is that there's no need now to check assumptions. I'm hearing a collective sigh of relief with that particular statement. We've been drilling in assumptions for a while, chapter 15 and 16. And so I think you guys have that understanding now. And so this is always going to work out for us in terms of buffer type solutions. So we can just go forward with assumptions and not worry about checking them with regards to buffers. So that's how you can solve for, the pH of a particular buffer, which would have an initial concentration of a parent acid or a parent acid and its conjugate base. Now, there is a subtle trick that we can also use, and that's known as the Henderson-Hasselbalch equation. Not the David Hasselhoff equation, the Henderson-Hasselbalch equation. All right, so this is something that we got to be very careful with because this works only for buffers. Students really like the Henderson-Hasselbalch. It's very sweet, it's simple, it's sexy, but it is only for one particular class of equilibria in terms of acid and bases, and that's for buffers. You can't use it for a weak parent acid question. You can't use it for a weak conjugate question. You can only use this specifically for a buffer question. And I know that students are going to like this equation and use it in other cases and then realize that I can't use it. So make sure that you understand that this is very, very specific just to a buffer system or a buffer style of question. And really all the Henderson-Hasselbalch is a derivation of what we see above, right? We see the Ka and what it's equal to. And so just with a little bit of manipulation, we can actually rearrange the equation and make it a little bit more simplistic for us to actually use within a question. So if I start with that Ka equation that we just had above, so that's what we had above, but let's simplify, or let's be a little bit more specific with it as far as, the molecules. So for this molarity of acetate, right, we're really just looking for that, that concentration of acetate, right? We have the concentration of hydronium, right, then over the concentration of our parent acid. So if I manipulate that a little bit, for instance, let's take the acetate and the acetic acid to the other side. Our hydronium ion, which we've now isolated, would be equal to the Ka times the ratio of acetic acid, parent acid, over its conjugate base. So just a little bit of simple algebra there. And what are we always tending to go towards here? Some facet of pH, right? Whether we're given it or solving for it. So let's put this in pH terms. Let's take basically the negative logarithm of both sides. So we're taking the negative log of my hydronium ion would be equal to the negative log of my Ka, right? Minus or plus the negative log of that ratio of the parent acetic acid to the conjugate base acetate. So we have a couple things we already sort of know here, right? That the negative log of hydronium is pH. The negative log of Ka is pKa. And what they do is they multiply the -1 through the ratio that we see on the far right, and that defines our Henderson-Hasselbalch equation for an acid-parent type of buffer. So you see, I just derived that from basically the Ka that we got from the ice table and all that. So this is an alternative method to solving buffer style questions. And since we don't have to worry about assumptions anymore, we can actually use this process. So there are two forms to the Henderson, and it really just depends on what you have in terms of your parent. So the first one, if it's a parent acid conjugate base buffer, you have the equation that we see above, namely that the pH is equal to pKa plus the log of the conjugate base over the parent acid. And while I didn't do this derivation for the other type of system, it's very much the same, meaning that instead of a parent acid, if we have a parent base, conjugate acid buffer, an example of that would be maybe, NH3 and ammonium chloride, right? That would be an example of a parent base and its conjugate buffer. Just like earlier, we had the example of the acetic acid and sodium acetate as the parent acid style of buffer. So we have something that looks very much the same for the parent base side of things, but now since it's a parent base, we're not generating hydronium ion in the equilibrium, we're actually generating hydroxide. So it's not a pH, it's really a POH is equal to a pKb, right? We have a parent base, so we have a Kb as opposed to a Ka. But we still have the same idea of the ratio in terms of that logarithm, that we're going to have the conjugate on the top or in the numerator, and then the parent, in this case the parent base, in the actual denominator. So those are our two Henderson-Hasselbalch equations, one for pH and one for POH. So you might be then asking, how does a buffer maintain constant or keep constant pH. So let's look at our two examples. So we have our kind of running example with our acetic acid and sodium acetate buffer. And so if we were to write that equilibrium reaction out, we would have something that looks like this. And so let's say I added strong base to this equilibrium process. Right, strong base would be, right, our source of hydroxide. And what is that strong base going to do? Well, it's going to react with the strongest acid. Right, it's going to react with the strongest acid that's actually in that buffer. So basically we could say that the strong base is going to react with the acetic acid, and as it does so and gets deprotonated to make H2O, right, in terms of this neutralization reaction, it actually produces the other component of the buffer. So it's like the hydroxide never has a chance to affect the actual pH of the solution, because the hydroxide immediately reacts with the parent acid form of the buffer, neutralizing the hydroxide to actually make H2O. We can also envision the other process by adding strong acid. If I add strong acid, right, or, H plus, again, it's going to react with the strongest base of the solution, and that would be acetate. And again, there is our neutralization reaction occurring. So if you add strong base, the parent acid neutralizes it, keeping constant pH. If you add strong acid, the conjugate base of the buffer neutralizes it, and again, you keep constant pH. You can do a similar example with a base type of buffer. So we talked about this ammonium and ammonium chloride being an example of a base type buffer. And so we would write it very much the same way by writing the equilibrium in terms of the parent. So there is our buffer. If I add strong acid, right, it's going to get neutralized and gets turned into the conjugate acid of the parent base. If I add then strong base, namely hydroxide, it gets neutralized. So the base addition gets neutralized by the strongest acid within the buffer. That would be the conjugate acid, ammonium, while a strong acid addition, or H plus, is going to get neutralized by the strongest base of the buffer. Right? And these are talking about the components of the buffer. Right? The components of the buffer being either the parent or the conjugate. So that's how buffers can maintain constant pH. I know it's a bit much there with these reactions that I'm showing you right now. In our next lecture, we are going to go into some examples and calculational examples and further reinforce this idea of buffers, how we can actually calculate pH of buffered solutions, and then how do we deal with, in terms of calculation, the addition of something strong, such as a strong base or strong acid, to a buffer that's already created, and how does that now impact the buffer and possibly the buffer's capacity.